Okay, so our next speaker is Ming Ho from Brown, and his title of the talk is Around the Motivic Monogeomy Conjecture for Non-Degenerate Hypersurfaces. Please, yes.
Okay, thank you for the introduction and sorry for the delay. I was suffering some internet difficulties earlier. So my talk today will be based on my recent paper on the motivic monodromy conjecture for non-degenerate hypersurfaces. So here's the main theorem that I'm interested in. So in my paper in particular, I managed to prove this theorem that was actually proven way back in 2011 by Lemma Yu and Tempoyan. And then recently reproved by Boris and Weiss in 2016 as well. And then recently I managed to give a different proof. So I should say that, so different proof from Lemma Yu and Tempoyan, as well as Boris and Weiss. So this theorem says that the local motivic monodromy conjecture holds for non-degenerate polynomials for n equals to 3 variables. And one remark I should say is this conjecture is actually already known for all polynomials in 2 variables. So by all, I mean even for degenerate ones. And this is due to various people. So Lusner, Weiss, and Button and Nikkei. And the outline of my talk is, first I will define what this non-degeneracy condition is. And then the second part of the talk, I will introduce this motivic monodromy conjecture. And then for the last part, I will state the main theorems. So these main theorems actually, as you will see later, they work for all non-degenerate polynomials, not just in n equals to 3 variables, but in any number of variables. Okay, so that's the main contribution of my paper. And then I'll sketch a strategy of the proof via an example. Okay, so now let me start. So first I'll talk about non-degeneracy. So first you fix a complex polynomial such that it maps, such that the vanishing locus of f contains the origin. So this is precisely condition, this condition here. So C0 is equal to 0. And then a definition is the Newton polyhedron of f. So this is defined as the convex hull of all these spaces. So these are like upper half spaces in some sense. So upper half spaces which are like centered. So upper half spaces like that are like emanating from this vector A, such that the coefficient CA is non-zero. So later I'll sketch some examples about to show what this Newton polyhedron of f is doing. So this is roughly, I should say, it's like the non-compact version of what some people know as the Newton polytope. So for the Newton polytope, what you do is all you're just taking is the convex hull of all the points. So all the points such that the coefficient of, so the coefficient CA is non-zero. So this Newton polyhedron, in some sense, it's some non-compact version of the Newton polytope. And the definition is, so for each phase of this Newton polyhedron, I take all the terms of the polynomial that are lying on the face var sigma. So usually I call this var sigma. So these are all the terms that are So all the monomials appearing in F that lie on the face var sigma. And then we say that F is non-degenerate if for every phase var sigma of this Newton polyhedron F, this vanishing locus of F var sigma is non-singular in the torus GM to the power of n. Okay, so
sorry. So your notation, your A is a power. So A is in capital N. This N is for natural number or whole number, including zero or not?
So you mean this A here?
Yeah. So A is in N, right?
No. So this A is a vector in n to the power of n.
So this capital N is including zero or not?
It's including zero, just that zero is always not going to be in the Newton polyhedron of F.
Okay.
Precisely because of this condition here. So zero, the origin is in the vanishing locus of F.
Okay. So okay. Yeah. Thanks.
So I'll give more examples later. So I recognize that this definition could be a bit complicated on first sight. So let me just mention a quick fact. So a quick fact is almost all polynomials are non-degenerate. So if you just fix any Newton polyhedron, then a generic polynomial whose Newton polyhedron is equals to that fixed Newton polyhedron is going to be non-degenerate. So I'll sketch more examples showing this later as well. So any questions before I move on?
So you should consider only compact faces.
Sorry?
You should consider only compact faces.
Yeah, so there's different ways to say this. So some people consider the weaker condition where F is non-degenerate only with respect to compact. Compact phases, sorry.
Yes, your notation is, your definition is a bit different from ours.
Yeah, so I didn't want to complicate the definition further, which is why I removed this with respect to compact phases. So usually people consider non-degeneracy with respect to compact phases if you're only interested in the singularity, if you're only interested in the singularity theory of VF at zero. But here I shall not complicate this condition any further. So here I just require for every phase. And most of the examples I consider later. In fact, it's non-degenerate with respect to every phase. Okay. So an example. So for example, if you consider this polynomial in two variables, then how you think about the Newton polyhedron is, so as you can see here, this term here corresponds to x1 to the power of 4. This term here corresponds to x1 squared times x2. This term here corresponds to x1, x2 cubed, and so on and so forth. Same for this. And then recall what the definition says. So you first consider this upper half spaces. Right? So you have all these upper half spaces. So you first take the union of all these upper half spaces. And then after you take all this union, you take the convex hull, and that's where you introduce all these edges. So this thing that I just shaded is precisely the Newton polyhedron. It's non-compact, so it goes on forever. And then part of the so I'm claiming that this polynomial is non-degenerate, and part of doing that is you have to check every phase. So for example, if I look at this phase, if I call this phase here var sigma, then F var sigma is x1, x2 cubed plus x1 squared, x2. Okay, so it's precisely all the terms that are lying on this phase. And then part of the condition is you have to check this is non-singular in the torus. So I'm claiming this is non-degenerate. So any questions before I move on to the next example? Okay, So a more complicated example, n equals to 3. So here, once again, if you plot down all the terms, so this is x1 square, x1, x2 to the power 4, x2 cube, x3, and x3 cube. Then once again, you take all the upper half spaces that are emanating out of these 4 vertices, and then you take the convex half of the union of all those half spaces. And what you end up is this, this Newton polyhedron with these coordinate hyperplanes as facets, as well as 3 facets that are not contained in coordinate hyperplanes. And then once again, I'm claiming this is non-degenerate. So for example, you have to check with respect to every phase, F var sigma, where var sigma is that phase, is non-singular in the torus. So for example, if I let var sigma to be this compact phase, then F var sigma is x1 squared plus x3 cubed. And then once again, you have to check this non-singular in the torus, and so forth. So you have to check it with respect to every phase. So these are 2 examples. Any questions before I move on? Okay. So let me give a non-example. So this example is a degenerate polynomial. So x1 plus x2 plus x3 square plus x2 to the power 4 is degenerate. So what I just sketched here is precisely the Newton polyhedron of that. Because if you expand this out, this is x1 square plus x2 square. And so forth. So, for example, all these terms here, this would be x3 square, x2, x3, and so forth. And then this polynomial is non-degenerate. I mean, this polynomial is degenerate because if I let var sigma be this entire facet, be this entire facet, so this whole facet here, then F var sigma is x1 plus x2 plus x3 squared. And this, as you can see, it's non-reduced. So in particular, it's going to be singular in the torus. So this is why this polynomial is degenerate. So one thing I want to mention here is non-degeneracy is in some sense kind of saying like your polynomial is written in the right coordinates where, so maybe I should rephrase this. So saying that a polynomial is non-degenerate is kind of saying that x1, x2, x3, and so forth to xn are precisely the right set of coordinates to study the singularity theory of them. So here, x1, x2, x3 are not the right coordinates because I can kind of like do a change of coordinates where, so if I let z be x1 plus x2 plus x3, for example, then this polynomial can be written like this. And then in some sense, this change of coordinates puts f in a form that is more puts f in a form that's more, what's the word for it? That's easier to, so puts f in a form that is easier for me to study the singularity theory of EF. So that's the rough idea of what the non-degeneracy condition is saying. Any questions before I move on? Okay, so that's a non-example. So now let me move on to an equivalent formulation of the non-degeneracy condition. So in fact, there's a cleaner way of expressing when f is non-degenerate in terms of what is called the dual or normal fan, usually denoted by sigma of f of this Newton polyhedron. So for example, if I use this example, this same example from earlier, so this example was non-degenerate. This was its Newton polyhedron. So now I'm going to roughly sketch how you construct the normal fan from this Newton polyhedron. So what you do is, in some sense, this Newton polyhedron has 6 facets. So this is 1 facet, the 2nd facet, the 3rd facet, 4th, 5th, and 6th. And with respect to each facet, you associate a normal ray to that facet. So for example, this facet here has the normal ray 1, 0, 0. This facet here has the normal ray 0, 1, 0, and so on and so forth. Right. And then let me call the normal ray of this facet U1. For this, it's U2 and U3. And then with respect to all these normal rays, you can construct a fan whose set of rays are precisely the normal rays to these facets. So this picture you see on the right is in some sense a cross section of the normal fan. So what you should think about this picture is, oh, sorry. So you should think that this is the origin, and then there are like rays shooting out from the origin. So this is the ray corresponding to E2. This is the ray that's generated by E3, and then there's a ray that goes backwards. So a ray that goes to E1, and so on and so forth. So there's a ray coming up to U1, and so on and so forth. And let me draw this. So something like this, and then I can't really draw for E1 and U3. And then how you form the remaining cones of the fan is, for example, if I look at this particular face of the Newton polyhedron, right? So this face here. So this face is the intersection of 2 facets of the Newton polyhedron, namely this facet and this facet. So dual to this face of the Newton polyhedron, I expect a dual cone, and that dual cone is precisely the cone that's generated by the rays that are corresponding to the facets so maybe let me say this better. So for example, if I look at this space, phi bar sigma, then this space is the intersection of for example, the facet that's corresponding to U1, and the facet that's corresponding to 1, 0, 0. So dual to this face, so dual var sigma, is this cone sigma that's just precisely generated by U1 and E1. Okay, so this face that you see, this cone that you see here is precisely dual to that face. And then you do it for every other face of the Newton polyhedron. For example, if I look at this vertex of the Newton polyhedron, then I expect a maximal cone that is dual to that vertex. Okay, and that maximal cone is precisely this maximal cone that you see here. Okay, because this vertex is the intersection of 4 facets. Namely the one corresponding to E1, U1, U2, and U3. Okay, so that's roughly a sketch of how you construct the normal fan. Any questions before I move on? Okay. So now that I've kind of sketched how to construct the normal fan, so this was the normal fan. Then, as you can see from this example, the normal fan is a subdivision of this upper quadrant. So if you know some toric geometry, then what this says is you can associate a toric variety to this normal fan. And not just that, that toric variety also admits a proper birational map to AN. Okay. And then if you know some toric geometry as well, you know that there's this construction that's due to Cox, where where whenever I give you a toric variety, I can associate to it a canonical smooth toric Artin stack, which I shall denote it by this, whose good moduli space. So if you're not familiar with this term, it's fine. Whose good moduli space is precisely a toric variety. So one thing I want to mention here is what's the point of associating, what's the point of working on stacks is that this toric variety is usually singular. But as I underlined here, this toric Artin stack that I associate to the toric variety is actually smooth. So there's some advantages of working on this smooth toric Artin stack. As you'll see in a second. So if I let pi sigma f, so capital pi sigma f, denote this composition, where this morphism is just a good moduli space morphism. So it's some like quotient map from the Artin stack to the toric variety. So if I let up pi, so capital pi sigma f denote this composition, then there's actually a observation that is noted by me and my advisor recently. So the following are equivalent. So for polynomial, for a complex multivariate polynomial. So f is non-degenerate if and only if this morphism that you see here is precisely what we call a stacky embedded resolution of the vanishing locus of f. So here what I mean by stacky embedded desingularization, what it just means is, so if I call capital pi as shorthand for this capital pi sigma f, then what this condition just says is the pre-image of the vanishing locus of f. This is precisely a simple normal crossings device on the Artin stack. Okay, so that's roughly what the condition is saying. Where simple normal crossings divisor on an Artin stack is kind of a slightly more general notion than what people call a simple normal crossings divisor on a smooth variety, for example. So this is some generalized notion of a resolution of a scheme theoretic resolution. So this condition here that you see is very concise now. So to check whether f is non-degenerate, all I have to do is use this morphism, compute the total transform of the vanishing locus of f and see whether I get a simple normal crossings divisor. And if it is, then f is non-degenerate. So this condition will come up later in my talk. So any questions before I move on? Okay. So now that I've introduced non-degenerate polynomials, I want to move on to the motivic monotony conjecture. So one thing I should mention is, so whenever people study the singularity of the vanishing locus of f at 0, then two natural objects of interest that come up are the following. So the first object is the local motivic zeta function. So z mod at 0 of f. So that's the first object. And then the second object is eigenvalues of some monodromy action on the singular cohomology of the Mueller fiber of f at points that are near 0. So one thing I want to say is for my talk, I'll only focus on one. So I don't have the time to talk about two. So I'll skip two actually. So if you're interested in two, you can always just search in the literature. These two terms, Mueller fiber. So I'll only focus on one. And then let me state the conjecture now. So the conjecture, or rather the local version of the conjecture states that if I give you any neighborhood of u of 0 in in C to the power of n, then I can consider monodromy eigenvalues of F at points in U intersect the vanishing locus of F. So that's one object, or rather a list of objects. And another thing I can consider is the poles of the motivic zeta function. And what the conjecture predicts is there's a relationship that's going on here. And the relationship is precisely given by this map. So what it claims is, if I give you any pole of the motivic zeta function, if I apply this map, then it gives me a monodromy eigenvalue. So that's what the conjecture is saying. Okay. So any questions about this conjecture before I move on? Okay.
I have a question. The previous page, this page, yeah. So do you need the F has iso singularity?
No. Yeah. So in fact, when F has isolated singularities, in some cases this conjecture is already known. So for example, weighted homogeneous isolated singularities, this conjecture is already known. So for isolated singularities, in some sense, some more results are known with respect to these two objects of interest. But this conjecture actually predicts for non-isolated singularities at zero as well.
But if
yeah.
Okay, I see.
Yeah, so this also applies to non-isolated singularity. That's the main thing.
So does the multiplicity of the poles also match with the multiplicity of the eigenvalue?
Yeah, so that's a stronger version. There's a stronger version saying that the multiplicity of each pole of the motivic zeta function is bounded above by the multiplicity of the monodromy of the corresponding monodromy eigenvalue. So that's a stronger version. Yeah, so I won't say anything about that. There's some work in progress that I'm doing right now that says a thing about says a thing or two about that. But that's not my focus for this talk.
Okay, thank you.
Okay. So as I mentioned, I will only focus on one. So the motivic zeta function of F. So this is the definition. It's kind of convoluted. I won't spend a lot of time on it. But all I want to say is that as you can see here, it's kind of looking like motivic zeta function because you are taking like the infinite sum of some list of things. Just that this infinite sum is happening in some localized quadratic ring of varieties, as you can see here. So it takes value in this ring, but I won't say anything more than that. So in fact, in the next slide, I'll give an alternate description of the motivic zeta function. So for now, if you don't understand this, it's completely fine. So this is one definition of motivic zeta function, but I'm more interested in the local motivic zeta function of F. So what you do is you just base change to 0. Okay, so here it's a localized quadratic ring of varieties over C instead of over AN. So that's just the difference. So I'm base changing to 0. So this definition is a bit convoluted, but in the next slide, I want to give an alternate definition. So here's a theorem. So if I give you embedded resolution of the vanishing locus of F above 0, so what I mean by above 0 is, so once again, you ask for this to be a simple normal crossings divisor, but not just a simple. So above 0 just means it's a simple normal crossings divisor only at points above 0. So this in some sense is is a weaker condition. So whenever I give you an embedded resolution of vanishing of the vanishing locus of f above 0, and then I let EI be the irreducible components of this pre-image. And for every irreducible component, I let Ni and ui minus 1 denote the multiplicity of that component in the pre-image and respectively in the relative canonical divisor of pi. So this is the relative canonical divisor of pi. Then there's a simple expression for the motivic zeta function of f. I can write it in this form. Where here now L is, so I forgot to say L is the class of A1 in the quadratic ring of entities. EJ circle here is some strata of the SNC divisor, of this SNC divisor. So it's some strata corresponding to this subset J contained in I. And then, of course, this is the pre-image of 0. And then we have this whole expression here. So I will see, so I explain this expression now. So this expression that you see here, most of the time people are only interested in the denominators. So this denominators here. So first thing I should say is this set of tuples, Ni nu I, this is called the set of numerical data of pi. And why people are interested in this set is because this set roughly corresponds to a set of candidate poles for the motivic zeta function of f. So what I mean by a set of candidate poles for the motivic zeta function of f, so there should be a 0 here. So what I mean by a set of candidate poles is precisely this relation that we see here. So notice that the denominators here are all roughly of this form. So whenever, so what this relation says is whenever I can write the motivic zeta function as some expression looking like this, with denominators that are looking like 1 minus L, and then there should be so there should be a minus here as well. So looking like denominators like this, then I call this set a set of candidate poles for the motivic zeta function. So roughly, if you think about it, it's just saying that whenever this is 0, so root of this polynomial is precisely minus nu I divided by Ni, and these things are precisely your candidate poles. Okay, so this set as I ranges over this index set, then I get a set of candidate poles for the motivic zeta function. Okay, so in fact as this term candidate poles suggests, some of these poles are actually fake, which I'll mention later. So let me now focus on the case of non-degenerate polynomials. So from now on, I shall assume that f is non-degenerate. Then as I noted earlier, because f is non-degenerate, this morphism, this canonical morphism here is a stacky embedded desingularization of the vanishing locus of f. So applying some stacky motivic change of variables to a variant of this morphism that you see here. So by stacky, I mean that in the earlier slide, as you can see here, y is a scheme. But I can imagine there's some analog of this theorem where y is an Artin step. It's a smooth Artin step. So applying the analog, that stacky analog, to some variant of this morphism, in particular, you see that there's a set of candidate poles for the motivic zeta function of f, given precisely by this. So this data that you see here is purely in terms of the Newton polygon of f, as you can see here. So what this set of candidate poles is I'm taking -1, and then I union it with this set of numbers, where each number is associated to a facet of the Newton polygon of f, that's not contained in any coordinate hyperplane. So this set is a set of candidate poles for the motivate zeta function of F. And now let me explain what this number is. So for every facet tau, as you can see above, this notation that you see here, so absolute value of u tau, this is the sum of the coordinates of the unique primitive vector, u tau. So by primitive, I mean that GCD of the entries of u tau are 1, is 1. So that's what I mean by primitive. So absolute value u tau is the sum of coordinates of this unique primitive vector that is normal to tau. So it's the normal vector u tau, normal primitive vector u tau. And capital N tau is defined so that if I take the affine span of tau, then this is precisely the equation of the affine span. Okay, so N tau is whatever that happens on the right-hand side of the equation. Okay, so these are like two numbers associated to every facet of the Newton polyhedron of F that's not contained in any coordinate hyperplane. So let me give an example now, because I recognize that this theorem is kind of convoluted in some sense. So a simple example. So let me go back to the running example. So this was the example I used earlier. As you can see, this Newton polyhedron has precisely 3 facets, not contained in any coordinate hyperplane. And with respect to each facet, I can associate a candidate pole. So how I do it is, if I take for example, if I focus on this facet, if I take the affine span of that facet, then this is precisely the equation of the affine span. And what I do is I sum up the coordinates of this normal vector. So 9 plus 4 plus 6, right? This was u tau from earlier. And then I divide it by capital N tau, which is 18 here. So that's u tau divided by N tau. And this number, if you sum it out, is precisely 19 over 18. And that's precisely the candidate for minus 19 over 18, as you can see below. And likewise, if you do it for the other facet, so for example, this facet would be 4 plus 1 plus 5 divided by 8. And that's 10 over 8, which is 5 over 8. And likewise for this. So 1 plus 0 plus 1 divided by 8. And you get 2. So I've associated 3 numbers to these 3 facets. And these 3 numbers together with minus 1 will form a set of candidate poles for the motivate zeta function. Okay.
So is it a coincidence that the numerator and the denominators always differs by 1 in this example?
Oh, yeah, I didn't notice that actually. So I have no idea what that means actually. In general, I don't expect that to hold. Yeah. Yeah, so I have no idea why this is true in this example. Okay. So here I've created a set of candidate poles, and as I mentioned, some of these candidate poles are going to be fixed. So here I've noted not every candidate pole actually induces a monotony eigenvalue of F near 0. So to establish the conjecture for F, one actually desires for a smaller set of candidate poles. So this is precisely the theorem in my paper. So if you take any non-degenerate polynomial in any number of variables, not just 3 variables, any number of variables, and then I take any set of B1 facets of the Newton polyhedron with consistent base direction. So this is some condition that I'll explain on the next slide. So condition on B. So roughly you should think if B satisfies some condition, then I can produce a smaller set of candidate poles. What I do is I take the original set from earlier. So this was the original set, but now I include this extra condition where I only take those numbers that are associated to facets that are not in B. So this is why this is precisely a smaller set of candidate poles. Okay. So I'll explain what this condition of B means in a second. So one thing I want to note here is for the case n equals to 3, this was actually previously established in Boris and Bayes. But their proof is very different from mine. So my proof is more geometric. It's more geometric in nature. Okay, so now let me explain this condition on B. So definition. So let me focus on one facet of the Newton polygon first. So a facet is called a B1 facet. If that facet has some apex, so some vertex V that I shall call the apex. So this apex satisfies the condition Vi equals to 1. So the ith coordinate is 1. So I realized I missed out something here. So I should say it's a B1 facet if there's this so there's this I, sorry, from 1, 2 to m, such that such that tau has a vertex V with ith coordinate 1. Sorry, one speaking.
哦，对对对，有，我刚一次先把它打开，然后选，没问题，刚刚是这样子，没错。哎，对，那维珍，我想问一下，就是那个。
Okay, thank you. Sorry. Yes, actually, I realized this definition isn't stated too properly actually. So there's this some index I such that tau has a vertex V with ith coordinate 1. So that's the first condition. And then what happens is, if I take the intersection of tau with EI equals to 0, so let's say tau looks something like this. Okay. So if I take tau intersect EI equals to 0, and then I take the convex tau of this phase of tau with V, then I expect to get precisely tau if tau is compact. So I can throw away this term. So this can be neglected if tau is compact. But if tau is non-compact, then I have to include this extra condition. So if tau is non-compact, then I have to include this extra condition where tau is actually equals to the closure of this convex tau. So this is just some subtle technicality, which I'll get to later. And then in this case, I shall call V an apex of tau, and I a base direction. So it's a base direction because, as you can see here, it's the base of tau, and then V is the apex. So it's like some pyramid with one apex. And then let me now state what it means for a set of B1 facets to have consistent base directions. So that means I can assign a base direction, B tau, to each facet, to each facet tau in B, such that whenever tau 1 and tau 2 intersect in codimension 1, so whenever tau 1 intersect tau 2, is a facet of tau 1 and tau 2. So whenever that happens, then I require that B tau 1 and B tau 2 to be the same. To be the same. So that's just some consistency condition on the base directions of tau. So let me give an example to explain these definitions. So let me go back to my previous example. So here, as I mentioned earlier, there's this Newton polygon has three compact facets. I mean, three facets not contained in any coordinate hyperplane. And actually, out of these three facets, two of them are B1 facets, and they are shaded in a lighter shade of gray. So as you can see here, it's this facet and this facet. And they share a base direction P. So that's because let's say if I focus on this facet here, this facet here, right? And if I take that facet, if I intersect it with E3 equals to 0, I recover this edge that you see here. Right? And tau is a B1 facet because if I take that edge and I take its apex, which is this vertex here, So if I take the convex tau of the edge and the vertex, I recover back tau. And likewise for this other facet, so tau prime, if I intersect it with E3 equals to 0, it's this edge that you see here. So tau, this is tau prime intersect E3 equals to 0. And then now if I take the convex tau of that base with the vertex, so the same rate vertex, I don't get back tau prime, but I kind of recover tau prime if I take the closure of that. Okay, so that's why tau prime is still a B1 facet. So the Newton polyhedron of F has two B1 facets, which I shade in a lighter shade of gray. And then if you recall from an earlier theorem, Theorem A from earlier says that I can recover a smaller set of candidate poles for the Motivik for the Motivik zeta function of F. So here I only take the number that's associated to the only non-B1 facet of F. So this is the only non-B1 facet of F. As you see earlier, the number associated to this facet is minus 19/18. And that's why this is a smaller set of candidates. So I throw out the numbers that are associated to this set of B1 facets containing tau and tau prime. Okay, so any questions before I move on? So if I'm not wrong, I have 12 more minutes, am I right?
You okay? You started late. Okay, yeah.
Yeah, I started late. Sorry, or 7 more minutes maybe.
Okay, yeah, fine, yeah.
Okay, so sorry about that. Okay, now let me give a non-example. So if you consider this polynomial now, its Newton polyhedron is given like this. So I've sketched the Newton polyhedron. It has two facets not contained in any coordinate hyperplane. But here they do not share a consistent base direction. That's because they both have this apex. But if I look at this facet here on the left, it has base direction 2, right? So this is precisely the base of tau. But if I look at tau prime has the base direction 3. And since 2 is not equal to 3, these two do not share a consistent base direction. And especially because tau and tau prime intersect in codimension 1. So whenever they intersect in codimension 1, I require the base directions to be the same. Okay, so this is a non-example. So let me go back to my main theorem. So theorem A, as you recall, whenever B is a set of B1 facets with consistent base directions, then if I throw out the numbers that are associated with the facets in B, then I get this smaller set of candidate poles. Now let me sketch the proof of my theorem. So my proof of this is geometric in the sense of the following theorem. So for B as stated above, I actually construct an embedded Q resolution. So this Q resolution is just some generalized notion of a usual resolution. So you should think about this something as saying like the pre-image of the vanishing locus of F is what some people might call a Q SNC divisor. So it's some SNC divisor quotient out by some group action by a finite group action. So I actually construct an embedded Q resolution of the vanishing locus of F above 0, whose set of numerical data are precisely the set of tuples that are inducing this set of candidate poles. So these are precisely the set of numerical data that are throwing out all those usual, so throwing out all the numerical data that are associated with facets that are in B. Okay, so it's geometry in this following sense. And now let me kind of return back to my running example to show you what's the main strategy of this. So main strategy of the proof of this theorem. So let me return back to this example. So as I mentioned earlier, this Newton polyhedron has two B1 facets with consistent base directions. So what I do in my proof is, so I drop this two B1 facets. So as you can see from previous slide, by drop, I mean, I take the intersection of the remaining half spaces. So this is one remaining half space. And then this is also a remaining half space, and so are those. So that's what I mean by drop. So I drop the two B1 facets. And by dropping it, I'm kind of like dropping the normal rays. So U2 and U3 are the normal rays associated to this B1 facet. So on the normal fan side, I'm kind of like dropping these rays. So after I drop this two B1 facets, I end up with this new polyhedron. Where this new polyhedron is actually a Newton Q polyhedron, in the sense that if I look at this vertex here, this vertex actually have rational coordinates. So this is a Newton polyhedron with actually vertices with rational coordinates. So by dropping it, I get some new Newton Q polyhedron. And then now if I take this new Q polyhedron, I get some normal fan, sigma dagger, which I've shown on the right-hand side. So let me go back to the previous slide. If you can see the difference, by dropping it, I'm kind of like dropping U2 and U3. And then I'm also introducing this ray, as you can see. This cone here. And then what's the strategy now is, now that I have a new normal fan, I just take the toric variety associated to that new normal fan. So once again, I have the Newton Q polyhedron, and because of that, its normal fan subdivides this upper half quadrant, and therefore this new toric variety also admits a proper bidirectional map to A3. So let me call it phi. And then let me just say this really quickly because of the lack of time. So now if you notice, right, so if I go back to the new normal fan, this new normal fan only has one exceptional ray, which is U1. And since the coordinates of U1 are 9, 4, 6, pi is actually very computable for this example. Pi is actually the weighted blow-up of A3 in the origin with these precise weights. So 9, 4, 6, precisely because U1 has the coordinates 9, 4, 6. And then one thing so in the next few slides, I kind of did the computation to show you why you get the resolution. But the rough reason why pi is a resolution is because if I write down the polynomial, so let me write down the polynomial. Right, so this was the polynomial, and the reason why this weighted blow-up resolves the singularity of f above 0 is because this polynomial, if I look at the terms, if I look at the leading terms with respect to those weights, so for example, x1 squared has the weight 18, x1, x2 to the power of 4 has the weight, has the weight 25. And then, in fact, if you compute the weights of the remaining terms, they are 18. And the reason why pi resolves the singularity of f above 0 is because if I take the leading terms with respect to those weights, right? So this is the leading term of f with respect to those weights. right? So the leading term of f with respect to those weights is precisely this polynomial here. And one thing you should note is this polynomial actually has an isolated singularity at 0. So in some sense, f is kind of like a weighted homogeneous isolated singularity at 0. And this is the rough reason why pi resolves the singularity of f. Okay. So one thing which I kind of justified to you is why pi resolves the singularity of f. What I haven't justified to you is why pi provides the right set of candidate poles. And that's really because I've dropped the two B1 facets. And by dropping the two B1 facets, in some sense, I dropped the normal ways corresponding to them. And therefore, I've also dropped some exceptional devices that were present in the original resolution. Yeah, so if people are interested, I can elaborate more on that. But if not, that's the end of my talk. So let me just go to the last slide. Okay.
Thank you. Are there questions or remarks?
Is there is there any connection with the Bernstein side polynomial, the roots of the Bernstein side polynomial with your candidate pose?
With my what?
Your candidate pose, your candidate.
Okay, yeah, so one thing which I never mentioned here is so the reason why these two theorems are enough in the case n equals to 3 is because once you remove all the candidate poles that are associated to the facets in V, then the remaining candidate poles actually are inducing eigenvalues of the monodromy action. But actually what's not known is, so even in the case n equals to 3, what's not known is the remaining candidate poles are actually roots of the Bernsteins of the polynomial. So that's not known yet. And there's no clear relation to what I'm doing actually.
Okay, thank you.
Any other questions? Yeah. So Minghua, I remember you also doing this resolution of singularity. So your current work and resolution and singularity, are there any connections or?
Yeah, so so there are indeed connections, but only in like the generic example, and kind of like once you so there's relation to my previous work on resolution of singularities, but only once you work with like a generic example, and only once you choose like the right log structure on AN. So in general, usually when people study non-degenerate polynomials, they would always use the full log structure. So the log structure associated with this divisor. But if you use this full log structure, in some sense, you are getting. So if you use this full log structure and you apply my previous work on resolution of singularities, it actually produces the wrong resolution for the monodromy conjecture. So in some sense, there's some relation, but it's still not clear to me what the relations are. So that's part of ongoing work as well.
Okay, thank you. So if there's no more question, let's thank the speaker. Yeah. So yeah, I guess that's all for today. We should see again in 2 weeks' time. Okay. Yes. Okay. Yeah. Okay. Thanks. Yeah. Okay.